and we'll address as many of them as we can at the end. Time permitting, we'll still open the floor to the audio voice link at the end of the presentation. However, we're not sure how that will go with, again, maybe 100 people on this presentation today. So if you'd like to take advantage of emailing in your questions, please send them to mzulpo@apexinc.com. You can see there on your screen. I'll be monitoring the incoming questions during the second half of the presentation while Chris Green will be presenting. Those questions we don't get to today on this webinar, if we do run out of time, we'll address those via email after the presentation and make sure everyone gets the responses they're looking for. So presenting today will be myself, Mick Zulpo, and Mr. Chris Green. Say hello, Chris.
Hello, everybody.
I'm the Director of Sales and Marketing here at Apex Instruments, while Chris is our Director of Business Development, and over the past few years, Chris has been focusing on our range of mercury products. Many of you might know Chris from meeting him at trade shows or visiting your site in person. Here's a quick overview of today's presentations and the topics that we'll be covering. First, I will talk through a brief history of the MATS regulation so we can have an understanding of how we got to where we are today. Next, we'll review the emission levels set in place by the MATS regulation. After this, we'll turn our attention to mercury specifically under MATS and how it's regulated under this rule. Chris will then take over and he'll take a look at PS12B, which is the performance standard identified under MATS as the guideline to monitoring mercury with sorbent trap systems. This will lead us then into looking at sorbent trap systems and the specific functionality and use of this technology under MATS. We'll quickly then review how our Apex instruments can offer you support in monitoring and reporting mercury under MATS. And then finally, we'll again address any questions or concerns that we have at the end of the presentation, time permitting. So let's start by looking at how we got to what resembles the MATS regulations that we see today. Back in 1990, the Clean Air Act required the EPA to conduct a study of the health hazards posed by hazardous air pollutant emissions from electric generating units. This report was to be presented to Congress no later than 3 years after the enactment of the Clean Air Act. So as a result, the study was presented to Congress in February of 1998. Moving forward a few years, on May 18th, 2005, the EPA issued the Clean Air Mercury Rule. On February 8, 2008, the D.C. Circuit Court vacated this Clean Air Mercury Act. A petition was filed with the Supreme Court by the Utility Air Regulation Group to overturn this decision. On February 25th of 2009, the Supreme Court denied the petition and the Clean Air Mercury Rule officially died. This, I know, is when a lot of you guys boxed up your monitoring equipment and stored it away until the beginning of this year. Or maybe for some of you it's still in boxes. We'll wait and see. 2 years after this denial, on March 16, 2011, the EPA proposed the EGU MACT rule. On February 16, 2012, the EPA published the Mercury and Toxic Standards Rule, or MATS as everybody knows it, establishing national emission limitations for certain hazardous air pollutants emitted from coal and oil-fired electric utilities. The MATS rule covers mercury, contaminants classified as hazardous air pollutants, acid gases, organic hazardous air pollutants, and particulate. If we take a look back to the Clean Air Act of 1999, which started all this, within it states that existing electric generating units must comply within 3 years after the effective date of any MACT rule that is put into place. This then puts the compliance date for MATS at February 16th next year. During the week of April 14th of this year, the U.S. Court of Appeals for the District of Columbia upheld the MATS rule against appeal. There is some rumbling of further appeals and the possibility of the Supreme Court taking a look at this ruling, but as far as I know, no formal request has been petitioned as of today. Even if this does occur, it must be noted that any decision to be handed down from the Supreme Court will be at least 18 months away, well past the compliance date of April next year. The moral of the story is that MATS is a reality for our industry. According to the EPA, this MATS rule will affect about 1,200 electric generating units across around 600 locations nationwide. So let's take a look at what the MAC rule states with regards to emission limits. There are differing emission limits for different regulated pollutants under the MATS rule. Even though our presentation day is specifically focused on mercury under MATS, I did want to share with you some of the limits of the other regulated pollutants as a point of interest. I'm sure you guys will all be dealing with these pollutants as well, so it's something that we all need to be aware of. I've made the assumption that most of you listening today are working with existing coal-fired units, and these are defined by the EPA as EGUs older than May 2011. So therefore, making that assumption, limits for these existing coal-fired units are 0.030 pounds per million BTUs or 0.30 pounds per megawatt hour of output for filterable PM, 2,000 pounds per trillion BTU or 0.020 pounds per megawatt hour of output for HCl. SO2 is 0.20 pounds per million BTU or 1.5 pounds per megawatt hour. For individual HAP metals, which are outlined in this regulation, you can refer to Table 2 of Part 60 in Subpart UU, which outlines these limitations. So turning our attention to mercury specifically under the MATS rule, they are determined by a couple of things. One is the fuel source that you are burning, whether it be coal or oil, and secondly, the allowed mercury limits under each fuel source are determined by the subcategory of fuel you are burning. There are also different limits whether the facility is continental or non-continental, meaning within the lower 48 states or not. The assumption again for this presentation and the information presented today is that your facility is within the lower 48. I would be happy to share emission levels for the non-continental facilities if anybody does need it. In our experience, most utilities fall under the non-low rank coal limits as outlined on this slide on the first row under existing coal-fired units. It shows that the mercury limits for such units is 1.2 pounds of mercury per trillion BTU, or expressed another way as 0.013 pounds per gigawatt hour. The different limits represent an expression of emissions based on either an input or output calculation. The regulation shows either of both of these reporting parameters can be calculated on page 9472 of Part 63. It is still unclear if by reporting emissions against one of these values, if you are then locked in to that reporting specification or you can change at will. We are yet to get a determination from the EPA on this particular question. Again, I would like to reiterate that these values on the screen currently are limits for existing EGUs defined as anything built or reconstructed before the 3rd of May 2011. These limits also apply to those facilities that are based within the lower 48 states. So let's look at monitoring mercury under MATS. You might have heard about quarterly testing for some MATS regulated pollutants such as filterable PM or HAPs. Unfortunately, mercury does not fall under the quarterly testing parameters. So what are the requirements for monitoring mercury under MATS? Well, by the power of deduction, we can come up with the obvious answer. constant testing or constant monitoring. So what does constant monitoring or constant testing mean? Part 63 states that mercury must be monitored using either an HG SIMS or sorbent trap monitoring system. Our line of expertise here at Apex Instruments is sorbent trap monitoring systems. Therefore, I will focus on what is required if you do use a sorbent trap system for mercury MATS compliance reporting. Once I've gone over the regulatory aspects of sorbent trap reporting, Chris will go over the sorbent trap technology itself and how you run the actual sorbent trap system. As a side note, Apex has about 300 mercury sorbent trap systems currently being used in the market. So, Section 5.2 of Part 63 addresses the use of sorbent trap systems under the MATS regulation. Specifically, it states each sorbent trap monitoring system shall be continuously operated and maintained in accordance with Performance Specification 12B in Appendix B to Part 60 of this chapter. The QA/QC criteria for routine operation of the system are summarized in Table 12B-1 of the PS12B regulation. Each pair of sorbent traps may be used to sample the stack gas for up to 14 operating days. This will make a little bit more sense when Chris speaks to it. However, I do want to say that in our experience, it is more common that we see sample runs of about 7 days, as PM buildup and other factors prohibit most sources from running a full 17 days on one pair of traps. So let's take a look at some of the aspects of PS12B in Appendix B that this section refers to. As a side note, PS12A, the performance standard for mercury SEMS, can also be found in Appendix B, Part 60. This image is taken directly from page 55044 in Appendix B, Part 60, showing the functionality of a sorbent trap monitoring system. We have added the sorbent traps here on the picture just for a point of reference on the system itself. Chris will speak further on how the system works, but to give everyone a basic overview, sample gas is pulled through a set of traps at the end of the probe where the mercury is collected on carbon media within the traps. The sample gas then flows through the probe, down the heated line to a moisture knockout, creating a dry sample. The sample is then sent to the dry gas meter, which records the sample volume so it can be compared to the volume of mercury collected to produce a time-weighted average value of the mercury sample for any particular period of sampling time. PS12B also states that sampling must be performed proportionally to the stack flow. This is simply done by taking a flow signal from the source, which is being already done under Part 75 anyway, sending this signal to the system and allowing the system then to control the sample rate based on the flow rate. Again, I'm not going to go into a lot of detail on this, as Chris will expand on this in his part of the presentation. So turning our attention back to Part 63, it outlines the requirements for certifying and keeping the sorbent trap system calibrated. Section 4.1.2 states that only a relative accuracy test audit, or everyone might know that as a RADA, must be performed for initial certification of a sorbent trap monitoring system. The acceptable reference methods for performing a RADA are listed in Section 4.1.1.5. So let's take a look at that, what section has to say. That section of Part 63 on page 9502 states that Ontario Hydro, Method 29, Method 30A, and Method 30B are all acceptable reference methods for certifying HG SIMS. We recommend performing a 30B, as in our opinion it is the simplest method, and taking into account that PS12B is based off Method 30B, it is the most like your solvent trap monitoring system. Other specifications outlined to perform the RADA are: the RADA must be performed at normal load. A minimum of 9 runs must be performed during the RADA. However, you can do up to 12 runs to allow you to discard 3 of those runs. Keep in mind, however, the regulation does specify that the up to 3 rejected runs must still be reported. It specifies that each run must be long enough to collect sufficient mercury mass on the carbon to be analyzed. This specific length will be determined by the source concentration of mercury and will be site-specific. RADAs must be performed annually with similar sorbent material as the reporting system is using, which in theory means using the same or similar type traps. Typically, traps used on a 30B RADA are 2-bed traps and are cheaper than 3-bed PS12B traps that you'll be using for everyday monitoring. Finally, this RADA must be performed on an annual basis, as I said before. There is a little more to this, though, than just that simple statement. So let's take a look at what that actually might mean. So right now, I have on the screen text from Part 63 that addresses the frequency in which the RADAs must be performed. A basic summary of this section is that the annual RADA must be performed within the fourth operating quarter of the yearly anniversary in which the solvent trap monitor was initially certified. It is assumed that you can perform the RADA anytime within that 4th quarter. For any facilities that do not run the system for any quarter within that year, you may extend the RADA anniversary date by the number of quarters that the system did not run. There is a limit, however, that you can only extend up to 8 quarters for this extension, or that it obviously equals 2 years. After 2 years, the RADA must be performed regardless if the system is running or not. If for some reason the facility is not operating for the duration of the 8th quarter in which the RADA must be performed, the RADA can be done in a 720-hour unit or stack operating hour grace period following that quarter. If you do perform that RADA within the grace period, the anniversary date of the next RADA then is reduced to 3 quarters instead of 4, so it's 9 months. However, if you do perform the RADA within that 8th quarter, then the anniversary date remains the same and will need to be performed within the 4th quarter or 1 year. I know this is a lot to take in. However, at the end of the presentation, I will let everyone know how you can get a copy of this presentation as a PDF with our speaking notes, so you'll be able to go back and take a look at a lot of this information that we're presenting to you today. So some other highlights worthy of note from PS12B in Part 60 are, we've touched on this point, but the system must be designed as per Method 30B and be able to sample continuously. The location of the solvent trap monitoring system, or where it will be sampling, needs to be in accordance with Method 1. Trap spike, which Chris will talk to later, but basically it's the spiked mercury level in the 3rd section of the trap, must be within plus or minus 50% of the estimated mercury that's going to be recovered. Again, Chris will talk about this in further detail shortly. PS12B also outlines specific QA/QC requirements for running a solvent trap system. Some of the highlights of the QA/QC outlined in the specification are: pre- and post-leak checks must be performed at the beginning and end of every run. Proportional sampling must be within plus or minus 25% of the stack volume. Spike recovery, which again Chris will speak to shortly and expand on. And then finally, equipment calibration checks. Another notable aspect of PS12B is that you're required to perform a Method 4 determination of stack gas moisture in conjunction with PS12B. Facilities under Part 75 are already performing this. However, Apex has petitioned the EPA to allow us to do volumetric determination of stack gas moisture by using the condensate collected by our system while performing the actual PS12B sampling. We have received permission for this exact alternative method under Method 30B, so we believe our petition hopefully will be granted and we'll hear from the EPA shortly. So now, after all this, you're wondering, is there any way I can get out of reporting mercury under mats? It all seems a lot. Are there any loopholes? Well, the short answer is yes. There are 4 types of units outlined in the regulation that do not have to report under mats. The first is units designated as a stationary combustion turbine, electric generating units that are not coal or oil fired and combust natural gas for more than 10% of the average annual heat input for 3 calendar years, or 15% for any 1 calendar year. EGUs that are capable of combusting more than 25 megawatts of coal or oil but did not exceed 10% of this input annually for 3 years, or again 15% in any 1 calendar year. And finally, EGUs are burning solid waste. This may sound promising to you, however, I would like to point out that the chances are that if you do fall within one of these 4 statements, your unit will most likely be reporting under the Boiler Act with a compliance date of September next year, or the Rice Act, which is already currently in effect. There are still several unanswered questions that we need clarification from the EPA before we can put all the pieces together. Some of these are, can I change the reporting between an input and output numbers at any time? This is referring back to the mercury levels as calculated against BTUs or gigawatt hours as we discussed in slide 9, which you'll be able to look back at if we share the presentation with you. What constitutes a startup or shutdown, and when do I actually have to start monitoring for mercury when this situation occurs? And what are the exact reporting requirements for the ERT? Hopefully we'll have some answers from EPA soon. So one more thing I'd like to mention is that there are qualifications to become LEED certified as a low emitter under MATS and remove the requirements for continuous monitoring of mercury. Chris and I actually recently did a webinar on LEED qualification with specific focus on mercury. Unfortunately, we don't have time to go into that again today. However, if after listening to what we've presented, you think your facility might qualify for low emitter status and you would like to know more about it, I would be pleased to send you over our presentation that we did a couple of weeks ago with our speaking notes so you can learn more about the possibility of LEED or low emitter status. Just shoot me an email at the address on the screen here and I'll be happy to share that presentation with you. Okay, that's enough from me. Now I'm going to pass you over to Chris Green, who will be talking about sorbent trap technology, how it can be perform the required testing for PS12B under the MATS rule, and then how Apex equipment might be able to help you with your project to become compliant by April next year. I'll hand it over to you, Chris.
Thanks, Mick. Good afternoon again, everybody. As you can appreciate, the development of the MATS rule, the requirement to be able to determine a means to measure, has been a long time in the making. I'm going to talk about the typical equipment used to meet the requirements of the PS12B performance standard. At Apex Instruments, we've been manufacturing source sampling equipment for 26 years, and we have a long history with the design and development of mercury trap samplers. Sorbent trap monitoring systems, an alternative to continuous analyzers, a method to capture a sample of the stack gas, separating the mercury for later analysis, for the standard developed by the EPA, offering a much lower cost option for mercury measurement. What is sorbent trap measurement? Well, Mick has already touched on what sorbent trap monitoring is about. Continuous repetitive in-stack sampling using paired sorbent traps with subsequent analysis of the time-integrated samples. However, the tester should have a knowledge and understanding of stack sampling methods including 30B. If we look at the key advantages of sorbent trap monitoring, a system is quick and easy to install, and importantly, no calibration gas requirements. The system is certified by the RATA test using a Method 30B system. But a sorbent trap monitoring system offers a significantly lower cost option for demonstration of regulatory compliance. So a pair of 3-section sorbent traps, sampling for typically 7 days. The system comprises a dual trap probe, sample pumps, a heated sample line, a control console, sample moisture removal, and high integrity test data collection. A typical picture of the hardware. Although there is a great flexibility in the equipment packaging to suit the process conditions and test application. I'll touch on this a little bit more later on. A sorbent trap. Well, that's typically what a sorbent trap, a 3-bed sorbent trap looks like. The test is always carried out by paired sample trap collection. The sorbent traps conform to the PS12B standard sampling analysis specifications. High concentration of iodine deposited on acid wash activated carbon ensure extreme mercury capture capacities without breakthrough for extended test periods in wet or dry stack emissions from coal-fired power plants. The trap configuration, section 1 will perform the primary capture of the mercury. Section 2 is for monitoring of any mercury breakthrough, and section 3 will be the spike section and monitored for spike recovery. The spike is close to a level to what we would expect to see in the stack. The trap analysis. Each carbon section is analysed separately. There are different analytical techniques available, however, the most common and quickest is thermal desorption. The total mass of mercury in the sample is the mass of section 1 added to the mass found in section 2. The initial RATA certification is well defined in PS12B. Most importantly, the use of the same sorbent media for the 12B system and the 30B RATA system. Both traps, however, must meet the QA/QC tolerance requirements as specified in the method. The sampling location must be representative of the stack gas conditions and free from stratification. When performing the sorbent trap monitoring, a pre-test leak check must be successful and proportional sampling to within plus or minus 25% of the stack flow rate, which is recorded in the test data file. A typical view of sampling underway from the source. Normally, the probe enters via a 4-inch or 6-inch flange. Here we see the illustration of the probe into the stack gas showing the cam-lock quick release technique for inserting and removing the probe. Important for the quality control aspect of the sample run, the trap IDs must be recorded. The system software actually reminds you about 3 times during the setup of the test run to record the trap identification data into the test file. But as a tester, it is always useful to carry a small notebook and manually record your activities and those trap IDs. From the standard, the analytical quality guidelines provide guidance on measurement, guidance on breakthrough, the tolerance levels, and guidance on the spike recovery. Similarly, the tolerance levels which will be acceptable. The standard provides great guidance on the relative deviation of the analytical result between the paired traps, which must be adhered to. So, for each measurement run, The paired traps must pass pre- and post-leak check, breakthrough tolerance, acceptable spike recovery levels, and proportional sampling throughout the test duration. For a successful measurement, we have to meet the QA requirements, but the standard does guide us what to do if only one trap meets the QA requirement. If we have only one trap with valid analytical data, we can multiply that value by 1.111 to enter as the missing trap data for reporting. The sampling system itself must pass a quarterly audit. The critical temperature sensors are checked to a reference temperature, and the dry gas meters are check calibrated against a reference flow device. This whole procedure takes about 1 hour. The reference flow device, however, must undergo an annual calibration recertification. The sample traps inserted into the sampling probe, it's easy and shown here. The weekly 7-day trap change should take about 20 minutes. However, we recommend that the profile runtime is set to longer than 7 days, perhaps 10 days, just in case you cannot get to the sample location to change the traps. For example, if the elevator breaks down, or personnel sickness, or some other reason. Seen here, we can see that some sources can offer a challenging environment for continuously extracting a sample. High particulate, wet FGDs, lime injection are some of the challenges for 7-day sampling. The right trap configuration to suit the sampling environment. Particulate, acid gas and moisture can cause sampling issues. This is where trap configuration can help with the process conditions. Additionally, trap shields can protect each trap. An illustration of the individual trap shields, ensuring no restriction for the pre- and post-leak checks. A dual trap probe and trap shield assembly, all ready to be inserted into the stack. Each side of the probe is identified as A and B. As a guide, always insert the lowest numbered trap into side A. Normal sampling and temperature of the stack up to around 300 to 350 degrees Fahrenheit is acceptable. Another solution is your sampling profile to make sure that you can sample for that 7-day period. Sample profile configuration to suit the measurement location. It's an additional aid to successful measurement program. Moisture has to be removed from the sample. We use the high-performance Stirling cooler, a closed system. The Stirling cooler offers high-efficiency moisture removal. Chosen for its ability to operate in extreme ambient conditions, for example, within an annulus where summer temperatures can be extremely high, and winter temperatures can be a little on the chilly side. Packaging of a sorbent trap control system. Generally, we offer 3 variations. A portable unit, a 20U enclosure with its own air conditioning and heater, and a wall or rack mounted unit. The wall mounted unit, as we've seen previously from the 20U housing, the wall mounted offers a smaller footprint where space may be at a premium, or perhaps space in the elevator accessing the sampling location is an issue. Each package variation offers the same operational functionality to meet the requirements of PS12B. A typical installation for a 12B sorbent trap system mounted at the stack sampling location within an annulus. The sample probe and control console mounted fairly close together. However, we do have some sampling location configuration variations. Generally, 3 typical system configurations. Our most common installation is everything at the measurement point. Space at the sampling location can be an issue, which is where the following configurations may suit the stack conditions. Just the probe and moisture removal at the sampling location and the control unit down in the SEM shack. Sometimes just the sampling probe at the sampling location, a heated junction box and heated sample line bringing the gas down to the SEM shack prior to conditioning and volumetric measurement. Key features of an automated PS12B type system as required by the standard. I think most probably high integrity data collection, making sure that none of the 7-day test information is lost for any reason. The control software, once it's installed on the laptop, it's accessed by an icon on the computer desktop. The main screen will connect the computer to the console, and then guiding the operator to the next screen by a highlighted next step box. Each screen, all the steps to operate the system are followed by the same intuitive highlighted box to follow, providing step-by-step guidance. The test profile records all of the general information which once added doesn't often change, but new profiles are easily added or edited. For example, if the test run duration is changed or any of the control temperatures or desired flow rate, it's easy to access that profile. What about alarm actions? What happens if an alarm occurs? What do you want the system to do? Stop sampling? Stand by? The profile will contain all of the test run information, the sampling location, the stack details. The leak check is fully automated for each test. Once successfully completed, that information is written to the test data file. During the test run, all the test run parameters and all the available run data can be accessed via the laptop. Alternatively, it can be viewed over the network anywhere over the plant. The test run data file is written to one of 99 memory slots, easily accessed, easily downloaded. At the end of the test run, we go through an automated post-leak check again. Once completed, the test data file is updated, and this is a good time to download that file. The test file is easily exported, either as a text file or CSV file, but also the test run data being passed into the plant data acquisition system, ready to be forwarded to the EPA via the ERT route once the analysis is carried out. A summary of that PS12B standard QA/QC requirements. Sampling, we must perform those leak checks. The sampling must be proportional to the stack gas flow. Analysis, we must see the trap IDs, relative deviation, breakthrough, and spike recovery. Additionally, that quarterly audit and an annual RATA test is required. Well, that's it from me. Thank you everyone for listening in. It was a very brief overview of sorbent trap sampling. Relatively simple, proven technology that's been in use for stack sampling for many years, but meets the requirements of the performance standard PS12B. We will be pleased to answer any questions in the remaining time, or if you require any further information or assistance, please do not hesitate to contact myself or Mick here at Apex Instruments. I'm now going to hand you back to Mick. Thanks very much.
Thanks for listening, everybody. We have had a couple of questions come in that we would like to address. Firstly, we'd like to maybe address the question of, let me just grab that question here. There was a question that came in, how do you determine mercury stratification in the stack?
Okay, well, not really mercury stratification, but flow stratification in the stack. We would need to, or test organisation or yourselves would need to carry out a flow characteristic test at the sampling location to make sure there is no swirl or anything wrong with the stack gas flow. But you know, if you need any further information on that, by all means, I can point you in exactly the right direction.
That would then lend on to another question that we did receive, stating that what is the probe length required for PS12B? That might be coming from some feedback that we've had that I'm not sure if you guys are aware, but 30B Lee testing does have a specific statement in that legislation that says you must be testing within the centroidal area of the stack to perform your Lee 30B testing. However, I'll hand it over to Chris to speak more on the PS12B testing area in the stack.
Okay. For PS12B, the probe tip, where the traps are located, need to be 3 feet or 1 meter away from the stack wall for any wall influence. Our normal probe lengths are 6 foot, 9 foot, 12 foot, but we can make longer. All our probes are made from hastelloy.
There's another question here that asks, is there an opportunity to input moisture stated during the flow rata and be used as a static number?
Yes. Yeah, it can take last validated moisture measurement, but I'll give you an update on that. We are pursuing EPA to give us an answer on this collected of moisture volume during the sample run.
There was another question about the analysis of traps and how that works. Most labs will typically quote around 7 working days for receipt of the traps and the analysis. There are specific regulations that come along with that in terms of chain of custody and things like that. But we do have a lab here at Apex, and we typically turn our traps around in just a couple of days with an emailed report back to you that you can use for reporting. We'll look at a couple more questions here that we may have got via email.
Okay, and just read that one. Yeah, no, normally we can take a direct moisture signal into the sampling console itself. So if there is a real-time moisture instrument giving us a 4 to 20 milliamp output, we can utilize that all the time. And that's quite often we do see that. Yeah, sure.
We've got some other email questions that are more specific to lead testing and things like that. We might actually address those because they're going to take a long time to explain here. We'll address those via email with some written responses. But anyone who's on the line who would like to ask a question over the voice link, please go ahead and we'll try to determine who we can hear talking and answer what we can.
This is Jen Boca from Tiger Creek, Ohio Valley Electric Corporation. I was the one that sent in the moisture content for flow rata question. I guess more what I was asking is that going to be allowed by EPA? Is anybody aware if that would be allowed?
Hi Jen, it's Chris. We have got confirmation from EPA on using the moisture we collect during a shorter run that is perfectly acceptable to use for the moisture determination. So we've gone back to EPA. Well, if we can do it for 30B, why can't we do it for PS12B? And we got a very positive response from them, but they've yet to come back to us at the moment. So we're still waiting, but we'll keep you posted. We'll keep you posted with any information we get from them.
Okay, thank you.
Thanks, Jen.
Does anyone else like to ask any questions? No? Great. Well, thanks everybody for joining us again. I'd like to reiterate the fact that we would be more than willing to share our presentation with everybody as a PDF, which will also show you our talking notes as well, because I know there's a lot of information there, especially at the start with regards to the regulation. If you were to send myself an email there, I'd be happy to share that with you. Also, if you wanted any more information in terms of the actual sorbent trap system itself, either a field visit, demonstration, or a site evaluation to see which particular sampling system might work for your location, please feel free to give Chris or myself an email, and we'd be happy to coordinate that with you. Thanks again, everybody, for your time, and enjoy the rest of your afternoon. Take care.